Okay. Hi everyone. Today I would like us to work on the center of gravity. What do you mean by the center of gravity of an object? Now the center of gravity is where the weight of that object appears to act, the overall weight. And when calculating center of gravity, there are three things you need to note using the principle of moments about both axes given or both points, both lines. Any line given. Then the second point is that if it is for the whole lamina, the whole portion, you are going to add their weight. If it's when a portion is removed, okay, we are going to subtract the main portion, the main lamina from what is removed. And so those are the 3 points. And equally to calculate that, we need to be aware of the center of gravity of a square. That's the middle, half the horizontal, half the length, half the width. And that of a triangle is 2/3 from the vertex. Okay, 2/3 the length of the height from the vertex. All right. And that of a circle, we're talking about if it's that of the weight, we're calculating the weight of the circle and the rest. That's the weight when the circle is involved. Now, we have this question before us. The uniform lamina shown above is in the form of a square ABDE, that's a GC question, of size 6A and an isosceles triangle BCD of height 6A. Find the distance of the centroid of the lamina from AE. That's the first part. Now, if the lamina is folded such that the triangular part lies on the square portion with the vertex C at the point F, where F is the midpoint of AE, find the distance of the centroid of the resulting lamina from AE. Okay. Now, when we have that question with us, to calculate that, we are going to look at the various portions. Is our work. Sometimes it's preferable to use a table where on the table the various portions are emphasized. If you have a portion, then we have the weight as well as a column for the distance as a coordinate of the center of gravity. Coordinate of CG. Here we only have the say from A. Okay, it will be from AE, it will be from AE. Now, which portion do we have here? We have the portion A, B, D, E. We equally have the portion B, C, D. And we have the overall portion A, B, C, D. A, B, C, D. Okay. Now, looking at this, looking at our diagram here, the weight, we're using the fact that if lambda, for example, is the weight per unit area, if lambda is the weight per unit area, it means lambda over area. Okay? Lambda is the weight. So lambda is the weight per unit area. It means that weight is lambda times the area. So to do this, to calculate the weight of this portion, this is a square. 6a times 6a gives us 36a squared. Now, times lambda, so we have 36a squared lambda. That of BCD is a triangle, half base times height. That's 6, half of will give us 18 a square lambda. That is the weight. Now the coordinate of the center of gravity from AE. This is our point here. This is the center of gravity. This is a square, is halfway. So it be you have here 3A. So from AE, from AE, this is our AE, the vertical is 3A. This is the center. Half of this is 3. Okay, we have 3A. Now BCD. That of BCD. If you're obtaining that of BCD, which we are talking about a triangle, that of BCD, from here to here, to reach from here to this point, 1/3 A, 1/3 6A is 2A. So from here, 2A plus 6A. If you take 2/3 from the vertex, 2/3 of 6A is 4A. It will be from here to here. This will be the 4A. This will be 4A. And if this is 4A, means from here to here is our 2A. Now from here, the center of gravity of this triangle to AE that I'm talking about means will be 2A plus 6A, which is 8A. And for the whole figure, since we are adding, we'll add here, it will give us 54A square lambda. And take note, please take note that since we are looking for AE, vertical axis, the y-axis, it means that the distance is the horizontal, the x bar. When it is about a vertical, about a y-axis, you look for the x coordinate. Now, having obtained this table, we can go straight to calculate the center of gravity of that lamina as a whole. Means you are taking moments about AE. And if you take moments about AE, we are going to have 36A square lambda times 3A plus 18A square lambda times 8A. And the sum total here is 54A square lambda times what? X bar. Which will make X bar the subject. X bar will be, after simplifying this, we have 36A square times 3A plus 18A square times 8A. When you sum all of that and divide by 54, we're going to have 14 over A. Sorry, 14 over 3. 14 over 3A. 14A over. Okay. Okay, the next part of the question is talking about being folded. Let's listen to the next part. Find the distance. Okay, no. If the lamina is folded such that the triangular part lies on the square portion with the vertex C at the point F, where F is the midpoint of AE. Now, when it is folded, this is what we are going to have. When it is folded, this is what we are going to have. It means if this is folded and all meeting here, we're going to have the shape now will be like this. All will come here. Okay, all of this will come here. This will be that line here. Okay, so all of this when folded means B, C, and D. All of this will now be cancelled and it will lie the way you have seen now that I've indicated in black. And when it is lying that way, the center of gravity of ABDE, still the center of gravity of ABDE from, if you are to include this portion here, the center of gravity will still be what? From AE will still be 3A. And the center of gravity of this triangle now which is lying here, we know that from here to here is, this is the vertex. When you are taking the center of gravity from the vertex to here, is 2/3 of that 6A. And 2/3 of 6A 2 over 3 times 6a give us 4a. So we have here 4a. So calculating now the new center of gravity. Calculating the new center of gravity, which we have x bar here, will simply be 36a, that's 36a square lambda, 36a square lambda times this one now, 3a, plus 18a square lambda times 4a, all of that being equal to 54a square lambda x bar, which when simplified is not a problem. When simplifying, x bar will be equal to 10a all over 3. That will give us the solution to that question. Okay, that's the first question. I would like us to look at this question. Okay, that said, I would like us to look at this regional mock question where we have our triangle here. Figure 1 shows a uniform lamina which is formed by cutting off the square HLMN of sides 5 centimeters with center O and a right angle triangle ECF from a uniform right angle triangular lamina ABC with side AB 12 cm, BC 21 cm. Find A, the distance of the center of mass of the remaining lamina from the sides AB and BC. Good. Now to do this well, we are going to have our table. So we write there the portion. We have the weight. Now we have the coordinates of center of gravity. Let me abbreviate CG from AB, as I have said, and from BC. From AB and from BC. Now the portion that we are going to look at is ABC. If you let lambda being the weight per unit area, okay, it means the area of this triangle ABC, we have half base times height, that's half of 12 centimeter times 21, which gives us 126. So the area of that triangle is 126 square centimeters. But we know that lambda is the weight per unit area. So the weight itself is 126 lambda. The coordinates of AB. Okay, of center of gravity from AB. From AB, this is our AB, which is vertical. This is our AB, which is vertical. From AB means we are looking at this coordinate. All right, from AB. Now, 21 centimeters. 21 centimeter from AB. 1/3 of 21 centimeter means, because we are looking for from here, this is from AB. 1/3 of 21 is 7. From BC, this is BC. This is the line, the horizontal BC. And if that is the horizontal line, from BC, this is our line, 1/3, if you are taken from BC, 1/3 of this of 12 gives you 4 centimeters. Now we have the other portion here, okay, LMNH is a square of 5 centimeter by 5. So we have 25 lambda. Okay. Now we have 5 centimeter. This is it here. If we take from AB here is 5 centimeter, indicated 5 centimeter also. Now to continue with that, since the question is telling us we have seen the portion, we have obtained that of LMNH ABC. We equally have E, triangle EFC. The area half base times height, that's which will give us 9. So we have 9 lambda. Now AB from CG, obtaining those coordinates. If you are to obtain that of that triangle, from here to here, about AB, from here to here is 21, and from here to here, it means this is 6, all of this remaining portion will be 15 centimeters. Because we have to obtain the center of gravity from this other point. Okay. Now from here to here, we are going to have 1/3 of 6 centimeters. But if you take from C, coming this from the vertex is 2/3. Remember, the center of gravity of a triangle is in a ratio 1:2. If you take here, you are going to have 4 centimeters. What will be left here will be 2. And the center of gravity is here, which is 2 centimeters from here, or if you are taking from here, it's 4 centimeters. And since it is 2 centimeters from here, it means all of these 2 centimeters plus 15 centimeters gives us 17 centimeters. And about BC, about BC from here to here, okay, talking about BC, the length means from this point to the center of gravity. If you are taking from this place, 1/3 of 3 centimeters, which is 1 centimeter. So we have 1 centimeter. Once this table is there, now look well here. Coordinates of CG from AB. If it is from AB, this is our AB. From AB, that's the y-axis. It means the center of gravity of the remaining lamina that we are talking about. This, you should note this. The remaining lamina that we are talking about. Since we are subtracting, we have 126, the larger portion, minus 25 minus 9. It gives 92 lambda. Now here, about AB, AB is the y-axis, so it means it's the x-coordinate, x bar. Because moment, we know what about the moment. BC is instead the x-axis, sorry, so it's the y bar that we're obtaining, the y coordinate of that center of gravity. And to do that, having obtained all of this, it means our center of gravity is simply, we have our distance here, okay, AB. We have our options, the various length here, which we are going to use to calculate to arrive at it. So when you are taking the moments, if you are taking the moments about AB, taking moments about AB, we are going to have 126 lambda times 7 centimeters plus, minus 25 lambda times 5 centimeters minus 9 lambda times 17 centimeters. All of that equal to 92 lambda times x bar. And when you multiply this, subtract all of that, what do we obtain? We're going to obtain our x bar. X bar will be 92 lambda all over 600, and those values there will give you 604 over 92 centimeters. And y bar will be similarly, for us to obtain that of y bar. If you are obtaining that of y bar, it means from our table, what are we going to obtain here? About BC, we are going to have, if it's about BC, we have 126. About BC, we have 126 lambda times 7 centimeter minus, times 4 centimeter minus 25 lambda times 5 centimeters and minus 9 lambda times 1 centimeter. All of that should be equal to 92 lambda y bar. And when that's simplified, we have y bar is equal to, y bar will give us 370 over 92 centimeters. So the center of gravity, the coordinate, we have 604 over 92 centimeter, 370 over 92. That is the center of gravity. That's how. Okay, having done that, we'll continue in subsequent videos to look at how to obtain the center of gravity when we have a curve. When we have a curve. But I can give you some little tips. If you have the curve, how do you obtain the x coordinate and the y coordinate? The first thing is, if you are giving a curve, a portion as a curve, you have to integrate from A to B. Let's say integrate to have the area. Then next, you look for x, y, dx. Means the function. Let's say you are given the function y equal to f of x. You have to look for x, y, dx with respect to the limits. You have that value. Then the next one again, to obtain a y bar. This will help us obtain our x bar. Our x bar will simply be the integral from a to b, okay, of x, y, dx all over this area. Whereas the y bar will be half from a to b of y squared dx all over area. Okay, so that gives you the coordinates. So if you are given a function, let's say you are given a function like if you are given a function x plus 1, it means here will be x into x plus 1. We integrate it from a to b. And here it will be x plus 1, all that squared. Integrate it. And evaluate the limit divided by the area. And the area will be y dx. Okay, so having done that, if you see a portion, they give you a curve, as I've explained again already, they give you a curve. They give maybe a curve y equal to x squared plus 1. A portion that is a curve, you use these three formulas to obtain your values. Very straight. It gives you the coordinates of the center of gravity. Alright, in the next video, happy learning.